There's a lot of misconception among people about the complexity of quantum mechanics. For example, if I search quantum mechanics on Google, the images I get are difficult to understand. Often, I come across solutions to very complex mathematical problems in picture form, or graphics that are impossible to comprehend. Among those images, we find various mathematical problems and graphics. Some people describe these as the essence of quantum mechanics. It's difficult for an average person, even someone with a background in physics, to understand this at once. Science is what we have developed to understand the complex things in the world. It shouldn't be complex. The mathematics involved can be complex, but the concepts shouldn't be. I'm going to prove that to you today. I'll explain the 3 most fundamental concepts of quantum mechanics in a very simple way today. All the concepts in quantum mechanics are built upon these 3 concepts. Alright, let's start. First, let's see what quantum means. The word quantum comes from the idea of quanta. Quanta refers to the fundamental amount of something in a system. For example, the fundamental amount in a pile of sand is a grain of sand. If you take a bucket of water, or any amount of water, the fundamental amount is a molecule. Similarly, if we talk more broadly, if we consider the universe, the quanta of the universe is the atom, because all matter in the universe is ultimately made up of atoms. If we take the word mechanics, mechanics refers to how a system works. So quantum mechanics refers to the scientific concepts that describe the behavior of the fundamental particle of everything in the universe. The atom, that is the behavior of atoms and subatomic particles. We know the universe is made up of 3 main things: space, time, and everything in it. As I said before, if all of the above are made up of atoms, then what is the science that can fundamentally describe the nature of an atom? All other sciences are based on this science. We need to understand that all other concepts in science are built upon quantum mechanics. This is a model describing the basic structure of an atom. We know an atom has a part called the nucleus. In the nucleus, positively charged protons and neutrally charged neutrons are clustered together. In addition, negatively charged particles, electrons, move around the nucleus of this atom. This is the general understanding. What we see from this is that an atom is made up of various particles. Many experiments we have done to describe the properties of matter can be explained by this model. But there's a small problem. If the nucleus has positive charges and the electrons have negative charges, how do the negative charges stay orbiting the nucleus? Shouldn't the electrons lose energy and fall into the nucleus? Shouldn't that happen? Positive and negative charges are opposite. There's an attraction between them. But that doesn't happen. That's actually the main problem with this structure. In addition, another problem is that while many experiments can be explained by this model, some cannot. For example, when we send these electrons as a beam, it has been observed that it doesn't have a particle nature, but a wave nature. The only way we can explain these 2 observations is to describe an atom as having a wave-like form. So there are 2 main models of atomic structure: particle and wave. Both of these structures are proven by repeated experiments. That means these electrons have a special ability to show both wave and particle nature. This is the first concept in quantum mechanics. We call this wave-particle duality. Electrons have the ability to be both waves and particles. Not only electrons, but it has been found that all systems have this ability. That's the first concept. Understand that. Let's look at the second concept. Imagine there's an object moving from A to B. If it's a normal object, we can think about an intermediate point while it's moving. Let's say that point is C. We can define the exact position of this system at point C, right? We can say it's a certain number of centimeters away from A. And we can also say its speed, right? It's moving at a speed of, say, 10 meters per second. So, when we take normal systems, especially systems at the scale we experience, we can define their position and speed very clearly. But in quantum mechanics, it's difficult. It can't be done. We call that the uncertainty principle. Let's see what that is. We talked earlier about electrons behaving like waves. We can define something called frequency for a wave. Frequency is actually the number of vibrations a wave. We can quickly define something else. The wavelength, that is, the distance between two consecutive points in the wave. Knowing these two, the frequency and wavelength, we can get a very clear and simple idea about the velocity of the wave. That is, like we said before, speed and position. We can define the speed of an electron very simply by looking at its wave nature. But the position, where is this wave? Is the wave here, here, or here? We can't say. Imagine a simple example, a pond with waves everywhere. We can define the wavelength and frequency of all these waves. But the problem is, where is the wave? The wave is everywhere. We can't define it as being here. But imagine I'm looking at a specific point in this system, say the defined position x, year, y. If a particle passes through this point while we're watching, we can say very clearly, at this moment, this particle was here, at the x, y position. But we can't say the speed of this particle is this much. It can only be seen for a very short period of time. So for example, imagine a drop of water falling into a pond. We know a wave is created here. But at the moment it falls, we can say this is the position, but we can't say anything about the speed of that wave, because a wave has formed. That same concept can be explained for an electron. If we say the position of an electron is here, we can't say its speed. If we say its speed is this, we can't say its position. This is the second concept in quantum mechanics, the uncertainty principle. Alright, let's go to the third and final concept. This concept is matter is quantized. That is, matter can be described in discrete quantities. Alright, look, now imagine we drop a ball from above. It hits the ground and vibrates repeatedly until it reaches a point of rest. Imagine I introduce an XY plane to this system, and I can mark the position of the ball's trajectory as x, y. Now we can say that any point within this path can be taken as x, y without any problem. X, y can be here, 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 here. Any point. Any point can be continuously defined by xy. Can we say that for xy, it can't be here within this path, it can't be here, it can't be here? We can't say that. Any point within this path can be defined as x, y. But after we come to atoms, it's not like that. This is the general structure of an atom. Within our normal experiences, when electrons move in an atom, there's a path the electrons move in, right? We can't come to any place we like on this path. The electron has to be in one of these energy levels. It can't be in a place between these energy levels. Now, we said about a ball, the energy can be anywhere, but it can't be like that for an electron. We call this the discrete energy levels principle, or energy is quantized. You can see in this picture that the electrons are either here, 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 or here, but they can't go to an intermediate place. That's the third principle in quantum mechanics. It's like this: if we push a ball along this surface, we can see that if there's an inclined plane, the ball can take any value for its potential energy. But the nature of atoms is that there are steps in between. That is, there are discrete potential energy levels. So it can be on the first step, it can be on the second step, but it can never be on an intermediate step. Clear, right? So this is the third point. All the concepts of quantum mechanics are built upon these three concepts. You can see that this is not difficult to understand. It's a very simple thing. But the mathematics involved can be complex again, but the concept itself isn't. Today I brought the three basic concepts of quantum mechanics. I think this will be helpful for you. Thank you very much to everyone who watched my video to understand these concepts a little better.